Hello students, this is Sanjana from Computer Science Department. In this class we are going to discuss about the continuation topic 2, counters, synchronous counters and other counters. In the previous class we have discussed about the counter, about the modulus counter and asynchronous triple counters and the 2-bit asynchronous triple counter and asynchronous decayed counters, binary sequence of the decayed counter, asynchronous up-down counters, and truth table for of the asynchronous up-down counters. Now, in this class, let us see about the synchronous counters. So, in synchronous counters, the clock inputs of all the flip-flops are connected together and are triggered by the input pulses. Thus, such that what are the flip-flops that you are taking, that all the flip-flops will change their state simultaneously. Parallelly they are going to change their state simultaneously. Here whatever the circuit that you are seeing below is it is a 3-bit synchronous counter. So if it is a 3-bit, what is the possible number of outputs that will get 2 power 3, that is 8. So here the J and K are the inputs, J and K are the inputs of the flip-flop 0 and are connected to the high, such that the flip-flop 1 has its J and K inputs. Why we are taking as J and K inputs? Why? Because it is a JK flip-flop. It is having the J and K inputs and connected to the output of the flip-flop 0, and the inputs J and K are flip-flop 2 are connected to the output of AND gate and is fed by the outputs of the flip-flop 0 and the flip-flop 1. Here if you have observed this figure, this is a 3-bit synchronous counter. So if you have observed this 3-bit synchronous counter, this is the first flip-flop and this is the second flip-flop. Here it is having the two inputs J and K, and by taking this output as the input of J and K, it is going to perform the AND operation here, and with that it is going to generate this output. So previously we have already said that if it is having the 3-bit synchronous counter, what is the possible number of outputs that we are going to get here? The possible number of outputs that we are going to get here is 2 power 3, that is 8, that is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. These are the possible number of outputs that we are going to get here. See, this is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 and 1 1 0 and 1 1 1. These are the possible number of outputs that we are going to get here. That is 2 power 3, that is 8. The next one. If you have observed this synchronous decade counter, it is similar to an asynchronous decade counter, just like the similar to the synchronous decade counter. It is similar to the synchronous decade. Synchronous and again it cycles to 0 again. From 0 to 9 it is going to start, and again it will be recycled to 0. This is done by forcing the 1010. 1010 means the value will become 10, and this is going to force the value of 1010 straight back to the 0000, that is 0 state. So this is also called as truncated sequence and can be constructed by the circuit. See, if you have seen the circuit, this is the first J flip-flop 0, and this is flip-flop 1, this is flip-flop 2, and this is clock signal that we are going to get here. So if you have observed this synchronous decade counter, here three flip-flops to give the possible number of outputs that here we are going to get is 8. So this is the clock signal. Here it is having the input, and this is the high signal that we are going to get here, J and K, Q and Q bar. So the Q naught is the output that we are taking, and here we are going to perform the end operation. After that, the output, whatever the output that is that we have got at the end operation, will be taken as an input. And here J and K are the by taking that input, here we are going to process the information, and again we are going to perform the end operation here. And after performing that end operation, we are going to take this J K values again, and again we are going to perform the end of the output. Again we are going to take another input here, that is the output of the first J flip flop, that is flip flop 0. For that we are going to perform the end operation. For these two we are going to perform the OR operation, and for that it is going to give the input J and K. Finally it is going to produce this output Q and Q bar. That Q bar is set to again here and get here. Finally the process will be repeated, that is up to 0 to 9. It is going to recycle again and again. It is going to up to 0 to 9, it is going to recycle, but it will say up to 0 to 9 it will be processed and recycles to 0 again. So this is done by facing the 1010 state back to the 00 state. So we can say this this one as a truncated sequence by constructing this circuit. So we can say this one as a synchronous decade counter. So if you have observed this truth table, this is a clock pulse that we have got here, that is 0 to 9, 0 0 0 0 that is 0, 0 0 0 1 that is 1, 0 0 1 0 that is 2, 0 0 1 1 that is 3, 0 1 0 0 that is 4, 0 1 0 1 that is 5, 0 1 1 0 that is 6, the value of 6. And next one is 0 1 1 1, this is the value of 7. Next one is 1 0 0, this is the value of 8. Next one is 1 0 0 1, this is the value of 9. So at this the Q3's values based upon this value, what are the binary values that we are getting here, based upon that the value of Q0, Q1, Q2, Q3 will be changed. So from this sequence on the left, from the left to right, we can notice that Q0 toggles and each clock pulse. It is going to toggle the each clock pulse, and Q1 changes on the next clock pulse. Each time it is going to change the clock pulse, that is it is going to set the Q0 value to 1, and the value of Q3 to 0. And the next one is Q2 changes on the next clock pulse each time, that is Q0 is equal to Q1 is equal to 1. The here the next one is Q3, the value of Q3, how the value of Q3 is going to change. See here the value of Q3 changes on the next clock pulse. Each time it is going to change upon the next clock pulse, that is Q0 is equal to 1, Q1 is equal to 1, Q2 is equal to 1, that is up to count 7. Or when Q0 is equal to 1, Q3 is equal to 1, the count value will become 9. So if you have observed this is synchronous up-down counters, the circuit of a 3-bit synchronous up-down counter and a table of its sequence are shown in below. So see, it is similar to an synchronous up-down counter. So a synchronous up-down counter is also has an up-down control input. We are having up-down control input, then it is used to control the direction of the counter. through a certain sequence. Through a certain sequence, it is going to take the counter. So if you have observed this up down signal, this is up down signal. Here you are having some clock signals, that is JK. That is here we have observed this one. Based upon this output, and here we are giving this input. Here it is going to perform the end operation here. Based upon this end operation, and again by taking this output here also we are taking performing the end operation. By taking the output of these two operations, here we are going to perform the OR operation. After that, it is giving the input to the again JK flip flop. By taking that input, after processing that one, it is giving the output here. So by take again here it is going to take the output of the end value here. For that, it is going to perform the OR operation. So again for that JK flip flop, it is going to give that value. So Q2 is the output here at different stage. Q0 is the first output, Q1 is second output, Q2 is the third output here. That is bitwise synchronous up down counters here. So from up to down it is going to process the counter. So if you have observed this truth table, it is also just like that. Here it is a 3-bit synchronous counter. So the number of possible values is 2 power 3. 2 power 3 means the value is 8. That is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. This is a possible number of output values that it is going to get here. So if we have gone for this up down ripple counters, in the up down ripple counter, all the flip flops, FF means flip flop, FF is a shortcut of the flip flop. So all the flip flops operate in the toggle mode. So either T flip flops or JK flip flops are used. The LSP flip flops, LSP is the least sequential bit flip flop, requires only the clock directly. Directly it is going to take the clock, but the clock to every other flip flop is obtained from Q is equal to Q bar, that is the output of the previous flip flop. So here the Q output of the preceding flip flop is connected to the clock of the next stage. Suppose if the upcoming is whatever the upcoming input it is achieved for this mode, the mode select, it is going to select the mode input M is at the logic 0, that is M is equal to, so down counting is M value is equal to 1 is equal to 1, then the Q bar output of the flip flop is connected to the next flip flop. So this will operate the counter in the counting mode. So here up to down in this up to down ripple counters, the flip flop to the clock of the next stage, and if the up counting is achieved for this mode, then the mode select input M is at the logic 0, and again if M is equal to 1, then the Q bar output of the preceding flip flop is connected to the next flip flop. So obviously this will operate to the counter in the counting mode. So this is the up down synchronous mode counter. See, an up down synchronous counter is capable of crossing either direction depending upon the, see, whatever the direction if we are going to choose, based upon the direction itself we can apply this operation here. So it can be capable of crossing either direction depending upon the control input. So up down synchronous counter, if you have taken this up down synchronous counter, it is giving this input like this. So after taking this as an input, this will be considered as the up one, and this will be considered as the down one. For this down one, we are going to, before giving the input, we are going to perform the negative operation here, and this is the flip flop 0, then this is the flip flop 1, and this is the flip flop 2. So for up down means, for up to down it is going to take the process. So here it is going to take the input. After that, it is going to process the operation. After that, by taking the two AND gates input, it is going to perform the OR operation, and again that one is given to the another JK flip flop. For that OR also output is taking as input for the two AND gates, and the output of these two AND gates is taken by this OR gate, and again it will be given to this flip flop 2, and the finally the resultant output is the Q2 and Q2 bar. This is the this is about the up down synchronous counter. Now let us see about this cascaded counters. Basically, cascading is a method of achieving the higher modulus counters. So if you want to cascade this higher modulus counters for the synchronous integrated chip counters, the next counter, whatever the next counter it is going to take, it is enabled only when the terminal count of the previous stage is reached. So large counters can be built by combining the smaller counters together. So the rollover signal is used to communicate when the should be rollover. So this is a more this is a if it is a most counter, that is 2 square, so it has to take the 2 flip flops. If it is a modulus 8 converter, that is 2 cube, it has to take the 3 flip flop for the roll. So whether whatever the modulus operation here that we are going to perform, first of all it has to take the input like this JK, and finally the output is given like this. Here also here the basic process here that is good that we are that here is going to perform is cascading. Why? Because whenever the larger counters can be built by combining these smaller counters together, then the rollover signal is used to communicate. So when this upper counter should roll over, finally the modulus operation here, whatever the modulus operation here, that is going to this cascading counters. So when the upper counter should roll over here, these are the cascading counters that you have seen here. So if the larger the counter can be, it basically it can be built by combining the small counters together. So all the rollover signal is used to communicate when up counter should be. So this is the figure related to the cascaded counters. Now let us see about this shift register counters. The two of the most common types of the shift register counters are introduced here. The ring counter and the Johnson counter. What are the two counters for the shift register counters? First one is ring counter and second one is the Johnson counter. So they are basically shift registers with the serial outputs whose were connected back to the serial inputs in order to produce a particular sequence. So these registers are classified as the counters. These are classified into counters because they exhibit a specified sequence of states. Okay, it is going to exhibit the specific sequence of the states. So if you have observed this ring counter is basically a circulating shift register in which the output is fed back to the input of the least significant stage. So this is the following 4-bit ring counter constructed from the D flip flop. So by this the output of the each stage, the output, whatever the output that is going to take here, the output of the each stage is shifted into the next stage of the positive edge of the clock pulse. So if this clear signal is high, all the flip flops except the first one, that is the flip flop 0, are reset to 0. So here the flip flop 0 is preset to 1 instead. All these ring counter is basically by a circulating shift register in which the output of the most significant stage is fed back to the input of the least significant stage. This is the basic thing. The output of the most significant stage is led to the input of the least significant stage. So if you have considered this bit ring counter, here this is the most significant bit. The output of the most significant bit is less to the input of the least significant bit. Up to that it is going to take the input and output like that. So this is the bit ring counter. So now if we have observed this clock, this is 0001. This up to here it is a 4-bit ring counter, that is 2 power 2. So the number of possible outcomes is 4. So 0 1 2 3, that is 0 means 0001, 0010, 0100 and 1000. This is the possible number of outputs that we are going to get here. Since the count sequence has the 4 distinct states here, it is going to have the 4 distinct states. The counter can be considered as a mod 4 counter. Only 4 maximum 16 states are you going to use here, by making the ring counters very inefficient in terms of the state uses. But the major advantage, whatever but the major advantage of the ring counter over a binary counter is that, so I not state the if you have considered about counters, it is a variation standard ring out here. It is having the inverted output at the last stage, feedback to the input of the first stage. So can call this one a ring counters. At end stage, the Johnson up to end stages, the Johnson counter yields a count sequence of length 2n. That is, if it is 2-bit 2n, that is 4. So it may be considered as a mod 2n counter. So that the circuit the circuit shows the Johnson 4-bit. For 4-bit we have taken this 4 flip-flops, 4-bit sequence, 4-bit Johnson counter. Here the state sequence for that is 000001001101, just like that is going to get here. So these are the applications of the counters. First one is the frequency counter, and next one is digital clock, next one is time measurement. This is a to D converter and frequency divider circuits and digital triangular wave generator. In these different stages, it is going to use the counters. These are the applications of the counters. Okay.